So, you ready? You want to do initial value problems for Sol? Because everyone's reading now, right? You're not wasting your own time and mine. No, you're spending time outside of class to actually do the homework. I mean, here's what I want to do in life. In life, I want to give you all A's, right? What do I end up doing? Not giving you all A's. Whose problem is that?
User error.
User error, correct. Now, a lot of you are well-intentioned, right? And I understand maybe this class is not super high on your priority list. There's no exams, so you feel like, well, there's no pressure. Just do it when I get to it. There's pressure now. Look where we are. This is week 9. This one doesn't count. We have 1, 2, 3, 4, 5 weeks of class. If you haven't learned more than half the material, then you're behind. If you haven't done all of the homeworks up to now, then you're behind. If you haven't done all of the pair programming up to now, then you're behind. If you haven't thought about your final project up to now, then you're behind. Right? How far you're behind is up to you. Yeah.
I know probably I don't know the question, but are you available free breaks?
Depends.
Slack.
Yeah, if you send me a Slack message, I won't have formal office hours, but if people are curious, you should jump on and I'll answer questions if I can, or we can throw an impromptu session. Let's say you're working with a friend, you're like, hey, I really want help on 8.2. We'll throw up Zoom and we'll work as though, is that okay? Okay. Yeah.
For some reason, it really.
You can. I tried it too. Same.
Like unless I go in there and look in a server or whatever, I don't get any. And that's like, from what I understand, some people have a big problem.
I'm not told you I use power notifications. I tried it.
Like it's actually blocked.
I mean, I don't, what kind of phone do you have? I don't know. I have notifications on my computer, on my phone. That's how I can respond to you guys.
What do you have?
iPhone 16.
Target the class.
I mean, I don't know if it's like different between iPhone and Samsung, but I assume it's the same app, right? You have the app?
Yeah, yeah.
Yeah.
I didn't get notification.
Oh, that's weird.
And I feel bad. It's like, oh, replied to you like 2 days ago. I'm like, oh.
I mean, if it's easier, we could do, email or something. What?
You could join the Discord.
No, I don't want to join a Discord. Because Discord's another app that I have to download. I don't need more apps in my life.
Yeah.
Yeah.
That's
That's correct. It's my class. I get to choose the mode of transportation. Okay. Okay, folks. Let's go. Okay, so Saul's gonna talk to us about initial value problems. Wait, where'd it go? Oh fuck, I lost my mouse. Saul, do you want me to present from the book? And then okay. So I'm gonna share my screen right now. And then I still haven't decided what we're doing for Wednesday. Does anyone want to present on Wednesday? I don't know. Maybe we'll look at the book. Um, We're basically done with 9 already, huh? We could go back and you could do, I mean, we skipped over these non-4 time centered space. So we could go back to 8 and we could do here. Do you want to do 8.5? Someone? Yeah. Full beams? Oh, let's yeah, sorry, let me go back.
Initial value problems, basically, what we're learning is we don't, we aren't given the end conditions, we're just given the initial parameters, and from there, we have to learn how to get the answer. So at the beginning page right there, it just tells you the diffusion equation for one-dimensional space. It talks about how it obviously only depends on X and T. And it goes on to explain, like, we can solve this how we have before. But, let's see if I remember. It does not work on initial value, because we have to know the end, like the end conditions. So it then goes to present the FTCS method. And what it does is
Let's pause for a second. Everyone but Saul, but maybe the people particularly in my fluids class, what is FTCS? Forward time centered space. What does that mean?
Four versus or 3 plus thing.
Good?
I guess I didn't say anything, but
Anyone want to help her out? What does centered space derivatives mean? Yeah.
central difference formula.
Central difference formula, right? Good. Okay, keep going, Saul.
So it uses the one-dimensional diffusion equation, and it specifies in this case that it's gonna be using evenly spaced grid points, though it also mentions that it is possible not to use evenly spaced grids. So then it just goes on to take the derivative, or yeah. And once we have found it with that in that equation, we plug it back into our fusion equation, and we get 9.20, which is our new equation. And then it proceeds to
So do we see this here on the left-hand side? d phi dt on the right-hand side, the diffusion, dx t squared or dx squared. And so dxt squared, this is centered in space, plus a minus a, 2 over the center. And the bottom is ddt. And then this is the stuff on the right-hand side that we've been solving, right? Yes or no? Okay, go ahead.
And then it proceeds to talk about how we can solve that equation, the 9.21.
This one.
And here they mentioned that we could use Euler's method. And it proceeds to ask, why would we use Euler's method compared to RK, which we have been using, which has shown that it's much more accurate. It proceeds to say that for second order, both RK and Euler's give the same error. So why, waste time and effort with using something that's more complicated to get the same amount of error when you can just use the Euler method and just, you have the same error and it's much faster.
Yep.
So from there, it describes the Euler method, which we have done before. And we get our equations. And we Taylor expand and throw, and we basically just get the full equation that we need, which is like for in H time step after some time T. And I think I did example 9.3 in.
You want to share? Okay.
So initially the problem is that we're given a steel container with 1 centimeter thickness all around is put into cold water, and then hot water is poured into it. And what we're trying to find is the temperature profile of the steel as a function of X from the hot to cold side. And here it also explains that for simplicity's sake, the base of the container is arbitrarily wide and the temperature profile is the same everywhere. So we use the same equation that we were using earlier, the diffusion equation, except this time it's for temperature. And we are given, well, first our initial values from here. And we are told the thermal diffusivity. And from there, this is just copying exactly from the example. We have the thickness of the steel, thermal diffusivity. We're going to be doing 100 divisions. And A is going to be our spacing of those divisions, or how much this, or no, the spacing of the grids. H is our time step, and then epsilon here relates to this part here. I don't know if you can see it, but it's the H times capital D over A2 or A squared. So since we know our spacing A, we already just square that, and we have our H as well. And we were given our temperature at the low end, but for the cold water, 0 Celsius. Our temperature, the initial temperature that the steel was on, which was 20 Celsius, and the high, which is the hot water, of 50 Celsius. And we said the problem also showed us that we are using these specific time intervals. We're going to check that at 0.01, 0.1, 0.4, 1 second, and 10 seconds. And T end is the end of our graph at some interval T plus some step epsilon. We initialize our arrays. And here we're basically telling it that at the zero, the first element or the 0th element is going to be where the hot water is. And this makes sense because we're going from hot to cold. Temperature always goes from hot to cold. And here is our loop. Here, this equation here is the one we were talking about earlier. This one here. And then we just go through the loop. And we going to be explained later, but for right now, I'm just going to say that this is just, right now, this is the if statements that are used to plot the graph. We can see how temperature is going from hot, and once it reaches steel, which we know is at starting at 20 degrees Celsius, stays constant throughout, and then it drops when it starts touching the cold water all the way to 0. So the rest of the explanation here, it's talking about why do we use the absolute or the difference rather than to just set T equals T1. And the reason is because they're not gonna equal each other at some points. So that would end up messing up our graph and not giving us the right value. So instead, we're using the difference to make sure that we're getting the right value. And a little thing here that I was talking about here was instead replacing the whole these two lines with this one line. And that's just me putting everything. So just replacing the for loop with this array slice. And we still end up getting the same graph. So it's in just a much faster way, because here it's 1.12 seconds, and over here was like 8.17 seconds. That makes a big difference when you're working with something huge. And here it keeps talking about how the graphs are looking here. And so that is basically just the FTCS method. Now we get into numerical stability. So it says that it works, the FTCS method works very well. However, there are times when it does not work very well. And one of those examples is the wave equation. So same as before, we're given the wave equation in one dimension, and we rearrange it so it's easier for us to work with. We use the FTCS method, but here we change it into two first order equations, which we have done before. And applying the same Euler's method, we get our two equations. And then it starts describing these three different waves. would at t equals 2 milliseconds, we get a pretty good graph. However, when we start adding more and more time, we start seeing that it does not look like a sine wave at all. So why is that? So here it says that why is it doing that? So what we can do is introducing something called the von Neumann stability analysis, which we will be using for the rest of for the other methods that are going to be showing up here.
Yeah, I mean, you don't need to go super deep here, right? Because we as computational physicists are not going to care as much about the mathematics.
Mhm.
If you want to give us a broad, high-level summary, that's great if you want me to do that for you. But go ahead and show the solution as opposed to trying to work through every part of the
Oh,
math.
yes.
Okay, cool.
Basically using I think what was I don't remember the PHYS the PHYS one. Through all that, it basically says that this little magic relationship right here, as long as if h is larger than this right side, it's gonna be numerically unstable and it's not gonna give you a good answer. On the other hand, if the relationship is true, you are gonna get a relatively stable answer. And it goes even more into detail about using the analysis and yada, yada, yada.
So for folks who are following along at home, not Saul, who actually did the reading, understands it, what are we saying by numerical instability? And what does that condition mean in words? Like not reading it out loud. What is it? What have we told the rocks, or what are the rocks telling us about this process? Go ahead and go back to that one. Nope, nope, nope. Go ahead. H is what unit? David, what is H? Elliot, what is H? T equals H, right? It's a time step. Okay, so the time step has to be less than what's A squared? Will? Or what's A? Anjali, what's A? Sorry, go ahead.
Position.
What do you mean position?
Position change.
Can I have a little bit more? The grid spacing, right? How far apart is your grid spaced? Anjali, what's D? Kevin? Diffusivity. What are the units of diffusivity? No one's memorized the units of diffusivity, right?
No.
Okay, let's go back 1 second. Can you go back one slide? Or not, you know what I mean? Sorry. Go back one more. Okay, go back one more. Go back one more. Okay, let's stop. Oh, no, go back one. Yeah, right here, right here, right here. Okay. dt. Awesome, right? D temperature, D time. So this would be like units Kelvin over second. Okay, over here is this Kelvin. So the Kelvins on both sides, they cancel. Over here, it's x squared, right? But over here, it's t. So I have to get rid of the x squared and I have to introduce the t. So what are the units of diffusivity? Meters squared. Very good. The units of diffusivity are meters squared per second. Okay, so let's go back. Let's see if we understand what the stability criteria is saying. in English words? Take a grid square. Okay, let's call it x squared. Diffusion happens in it in a certain amount of time. The diffusivity, in fact, has units of meters squared per second. How much is something spreading? How much is something increasing meters squared per second? Good. That necessarily has a time once you, for example, take the grid spacing squared and divide it by the diffusivity. So what does this say on the right-hand side?
It's the grid space, for efficiency.
Good, but what does that mean?
Right?
Right? And what? There we go. That is the physical meaning. So what is the requirement on the computer? Read that now in English.
Which step is a contained within the time. For
Right.
example,
You have to be able to have a computer resolve the physics, which means your time step must be smaller than the time it takes to diffuse. Okay? Not to diffuse the entire fluid, but the characteristic time scale for diffusion, which is represented by the grid spacing, which you choose at home, and the diffusivity, which is a property of the thing you're trying to simulate. Right? So now two of the things that you choose at home, the speed, how many time steps you take, and the grid spacing, how many little dots you have in your array, those need to be related in order to be numerically stable. Because if you don't relate them, your code will explode. Right? So I'll just show you how it goes. And if you're working in fluids, you've already seen the code explode. Right? I'll show you at the end. Go ahead.
And then it also proceeds to talk even more about using the analysis to find the stability, using matrices, linear algebra, eigenvalue. Basically saying the same thing. Just it's basically just trying to confirm even more that that relationship is true. And here we get the implicit and Frank Nicholson methods, which is two different ways that we can approach problem of numerical stability.
So I think you're on a roll. You've already been standing for almost a half an hour. And I think this is going to work really well if we can give it to whoever wants to do other forms of differentiation. Because once we've seen an implicit versus an explicit differentiation scheme, I think that's really going to help. Because this word right now doesn't mean anything to anyone until you've read chapter 8.5. So let's leave this section, which is 9.33 for Wednesday. And we're going to just try and do the problem, the diffusion problem today. Okay. Any questions before we get started? Okay. So I'm going to say the same thing that I've been saying. Okay. First thing is you should be reading before class. Read what we're going to do as though you're going to present. You will waste less of your time here in person. 2, work outside of the class. Okay. You have spring break to catch up on whatever you haven't caught up on. I know there's some people whose homeworks are not up to date. I know because I can see them, right? You will fail this class. And it sucks because it's a complete waste of your time. It's a complete waste of your money. It's a complete waste of my time. Right? I mean, I get paid either way, but I would much rather help you be successful. Right? I don't want you to like be so happy and then I have to fail you and then I'm like, well, I feel like an asshole. Like, don't do that to me. Okay. If you're not going to do it for you, do it for me. Okay. Third thing, if you work with someone else or if you work with groups or if you use the book or if you use a resource, don't forget to cite it. Because if your stuff looks really good and you don't know how the fuck it happened, guess what that looks like to me? Correct. Say that louder for the group. Cheating. And cheating is bad, not good, yucky. But the funny thing about coding is if you use someone else's code and you cite them, not cheating, right? But if you use someone's code and don't cite them and don't know how it worked, bad. You use someone else's code and cite them and know how it works, good. Okay. Questions, comments, concerns? You're 9 weeks into a 16-week class. That means you're more than half competent, right? Okay, so the next 6 weeks, we're going to become super, super good at what we're doing. Okay. I think so. It's going to be the temperature one, I hope.